Okay, so continuing with our discussion about how modern SoCs can be used effectively, we would like to understand a bit more about the hardware-software interfaces that are used in such systems, right? So first of all, why are we even talking about this separation between hardware and software? Well, modern digital systems, as we already discussed, typically have hundreds of millions to possibly billions of transistors. The hierarchical design strategies that we have discussed so far are fine as far as the structure of the system is concerned, right? I mean, in other words, we know how to break a large system down into components and then those components into submodules and so on until we are at a point where we can design each individual module. But to actually use such a system, you need some kind of programmability. That's where software comes into the picture, right? And modern systems basically have an extensive interplay between the software and the hardware, which means that you need various different degrees of abstraction out here, right? At the hardware level, typically we are dealing with individual registers, possibly with some kinds of buffers or directly with memory accesses. We can get to allocate certain blocks of memory and use them, but that's it. You are literally just dealing with chunks of linear memory. The firmware, on the other hand, provides you with one higher level of abstraction. It basically says that you have some slightly low level code that directly controls various kinds of hardware. You have device drivers which are effectively sort of building up what's called the operating system layer, right? They interact with the hardware, but they provide an abstraction to the software, which for example allows you to say, you can call a function like send byte to UART rather than going in there and directly setting the individual registers in the UART, setting it to transmit mode, loading the buffer, then activating it and so on. All of that gets encapsulated into a function which looks like send byte to UART, or at an even higher level it might just say print to console, which in turn will know that the console corresponds to this particular UART. It sort of abstracts that information away from you. All of this is basically also captured in what's called the hardware abstraction layer, right? It's a set of software functions that provide you with a standardized interface to the hardware. The application software that we actually interact with builds on top of all of these layers, right? So when you, let's say, run a web browser, right, it is, as far as we are concerned, we can, we have a URL bar, we can type something over there and then something gets displayed on the screen. The fact of the matter is the URL bar is something that needs to get displayed onto a location in memory, which means that a picture of what needs to be displayed on the screen needs to be maintained in memory as part of what's called the frame buffer. There has to be hardware which takes data from the frame buffer and puts it onto the screen, which lights up the different pixels in different ways. There has to be something which interacts with the keyboard and the mouse, which allows you to click on the URL bar and then to type something which shows up in that URL bar. There has to be a network interface which says, okay, this is actually a URL, now find out how to communicate with this over the network and get the data. In other words, all of that is abstracted away at the level of the application software. We just write code that says, draw something on the screen, put something, interact with the keyboard and mouse, and then interact with the network. And how exactly each of those interactions happen is hidden away behind the hardware abstraction layers and the device drivers. Now all of this, one of the ways by which we have looked at it was of course what's called the memory mapped IO, right? We have already seen examples of this where we take a memory address space allocation and break it up into, we use some kinds of either base and offset addressing techniques, register maps and bit fields and so on, and various kinds of register level access patterns, right, in order to directly be able to communicate with various registers that are present inside the peripherals. Now, as mentioned earlier, there are so-called direct IO instructions in certain kinds of processors, but these are not very common. The memory mapped interface is a more generic version and a more sort of a better abstraction in a lot of ways than having separate instructions for IO. Although it may be that for some specific kinds of applications you might find that having a separate set of instructions whose only job is to communicate with IO peripherals may also be useful, right. So keep in mind that all of these ultimately come down to various kinds of specializations that can set your design apart from somebody else's, right. If you find that there's an application where having separate IO instructions makes more sense than having a memory mapped interface, then that might actually give you some kind of an edge or superiority over other kinds of designs that exist. Now, of course, when you want to implement memory mapped I/O, there are various things you need to take into account, such as how do you do address decoding, how do you manage the compatibility between the different bus protocols or between the different module interfaces that are handling the bus protocol, right? And certain things such as memory protection and privilege levels that we have not talked about in the course on digital design, but which are important from the point of view of things like operating systems. Register interfaces is something that we have already seen, right? Effectively what happens is that each peripheral has a certain set of internal registers which allow you to programmatically control the behavior of the peripheral or to check the status of the peripheral. And most of the time this is done through some kind of bit field organization. The point is that for the most part the peripheral by itself has certain status bits, but from the software point of view it makes it, or rather it is not easy to go and check individual bits directly. What is done instead is to sort of group several of these bits together. So for example, I have a status register maybe inside a UART, which this is just an example, right? This is not the only way that UARTs could be defined, but I might have something which says that bit 0 indicates that the receiver is ready, bit 1 says that the transmitter is empty, right? You don't have any data and therefore if you want you can write more data into it. Bit 2 could be a receive overrun, it's a status signal, which all of these are status signals which sort of say that which indicate to the software by reading this these bits whether any one of these conditions has occurred, right? Bits 3 to 31, I mean, the reason why something like this happens, reserved bits, is simply because we chose to sort of take a block of 32 bits and say that all of them are going to be treated together. In reality, I only care about 3 bits over here, right? Similarly, I can also have control where it allows me to sort of sometimes possibly read, but for the most part write. I should be able to write into this to enable the UART. I can then sort of say whether the interrupts are enabled, what is the baud rate to be used and so on. Those can be sort of configured by writing into these registers. So as you can imagine, from the hardware point of view, we are interested in individual bits. From the software point of view, we convert them into what are called bit fields, which are the bits inside a particular register, right? And that is because software works at a granularity of bytes or 32-bit words, whereas hardware may be interested only in individual bits. This is where the interface, the register interface between hardware and software comes into play. Now again, from the embedded systems course, you would know about the idea of interrupts and where they become useful. They are primarily used for efficient use of processors, right? They allow you to avoid waiting for long running tasks. Let's say that I have a task which is going to take many hundreds of clock cycles. The processor, rather than sort of initiating the task and then waiting until it has completed, can sort of just initiate the task and then move on to other operations, and when the task is completed it will get back an event, an interrupt that wakes up the processor and gets it to respond again and do whatever it needs to do next. This is especially the case, for example, when you have things like the UART, which is operating several orders of magnitude slower than the processor. For example, if I have a processor, even a microcontroller running at 100 megahertz, but a UART which is running at like 9.6 kilobits per second, that's like 3 orders of magnitude or nearly 4 orders of magnitude speed difference. So by the time one bit has been sent out on the UART, the processor would have managed to complete 10,000 clock cycles, right? So rather than waiting, what the processor would do is just dump some data into the buffer of the UART, go do some other work, and when the UART has finished transmitting the bytes that it needs to, it can send back an interrupt to say, okay, now I am free again, you can send more data if you want to, right? So for handling these kind of things, your processors need to have separate interrupt controllers. From a software perspective, we have already looked at it in embedded systems. You have interrupt service routines, and of course you need to worry about things like the latency of interrupts and so on, right? And how these get implemented inside the processor is you need to have custom digital hardware which responds appropriately, right? So whatever we talked about the CPU interface so far does not really mention interrupts, but if you think a little bit about it, it's possible to integrate that. Once again, that's sort of left out of this the scope of this course in the sense that that's probably more appropriate for a dedicated course on processor architecture, right? Although if you think about it, it should be possible for you to design a interrupt controller with the knowledge that you have of how the CPU works right now. Moving further along the kinds of things that become useful in the context of hardware software communication, right, or the hardware abstraction, is direct memory access, where basically what we are interested is we want to be able to transfer data, right. The earlier example I gave was about how a UART is several orders of magnitude slower than a CPU, but well, so is memory, right. Especially let's say that I want to copy a large chunk of data from one location to another. Now this large chunk of data could be anything. Let's say you are editing a text file, right? You want to copy the bytes in that file from one location in memory to something else which corresponds to the temporary storage in which you are working, right? The interesting thing is even a fairly simple text file could be a few kilobytes in size, which means thousands of bytes, and copying that in memory itself is going to take thousands of clock cycles. Rather than the CPU being completely occupied during that time, it makes sense to see if there are certain kinds of DMA or direct memory access hardware controllers, right, which can directly take care of, for example, copying a chunk of data from one block of memory to another block of memory. Now this becomes even more relevant, let's say when you are trying to transfer data from memory into a peripheral, for example, a video interface or a Ethernet card, right? Or maybe you are getting data high speed on an Ethernet and then you need to copy it back into the memory so that it can be processed. And in some cases you might even find that you have a peripheral to peripheral kind of communication, right, directly bypassing the CPU altogether and going directly from one peripheral to another. If you have a custom sort of hardware, right, that specializes in moving data around, right, it can take care of all of these things and leave the CPU free to do other things. Of course, you need to write the software appropriately so that the CPU is finding something that will keep it busy, right, and does not sort of get stuck unnecessarily. But as long as you know that it's there, it should be possible for you to do something of this sort. There are many advanced features in DMA which again some of which you might have seen in or at least seen some aspects of in embedded systems, but we are not really getting into detail here. It's just that these are things to be aware of. The bottom line is modern systems use huge amounts of data and need the ability to transfer these data around rapidly. So direct memory access becomes a crucial part of any large system. Moving and keeping in mind the abstraction, the idea of abstraction that we have been talking about, device drivers are essentially a software abstraction that allows or help us to control hardware peripherals, right. What a driver needs to do is things like, for example, initializing and configuring hardware, transferring commands into the peripheral or transferring data, right, how to handle interrupts, how to detect and recover from errors, as well as some kinds of power management capabilities, right, which could include things like turning off a peripheral when it's not being used and so on. What a driver does is very rarely to sort of do this automatically. It provides a set of functions to the application software or to the operating system, which can then be used in order to do this. Now the same thing could have been achieved by directly writing into the registers of the peripherals that we have, but all that this provides is a set of uniform functions that make it easier to write code of this sort, right. Typically we have some kind of a layered architecture. We have something which is hardware specific, then common bus operations, operating system functions, and finally application specific or application facing programming interfaces. For example, opening and closing files or reading from a network interface, all of these could be application facing APIs, which are in turn using the OS abstraction layer, which in turn talk to the bus layer and then finally to the devices at the hardware abstraction layer. The hardware abstraction layer in turn is sort of abstracting out the hardware into a set of common functions, right, ultimately leading into the idea of operating systems, right. There are several common abstractions that we would come across it. Again, most of this would be discussed in the section on embedded programming, right. And ultimately the typical driver stack in a modern system would look something like this, right? This division that we have over here is very commonly thought of as the operating system divide, which basically says that below this you have something called kernel space, the operating system kernel, and above that is where users typically tend to write code, right? So let's say that you are using a Linux operating system, you very rarely go in there and write functions directly at the kernel level, but as you can see, there is a lot of functionality that happens down below that, right? So for example, you have individual kinds of drivers that deal with various kinds of devices. It could be network devices, it could be block and character, typically relate to either disk or maybe keyboard, mouse, UART kind of peripherals. This is a very abstract class of devices, right? But the actual devices, let's say that you have a solid state disk versus a spinning hard disk, right? Both of them would be considered as block devices, but then would need specific device driver code underneath that activates the specific kind of communication that you need. In turn, that then usually goes down to bus level drivers like PCI or USB and so on, right, which needs to then go down to the hardware abstraction layer, and this is the point where you are actually talking about memory mapped I/O. You need to know the addresses of individual peripherals, and finally of course you are talking to the physical hardware. At the OS level, we have much higher levels of abstraction. We talk in terms of files or sockets or inter-process communication, which is then further abstracted to a point where you can actually talk about applications that literally draw windows on screen or talk to databases and so on, which are in turn building up on the abstractions that are provided by the lower layers. So there are a number of interface mechanisms that you need to be aware of when we are talking about the hardware software interface between and as parts of a modern system, right? There are many different layers in these stacks. We have a number of different design principles that we have looked at in various different contexts. From a hardware point of view, we are always dealing with registers. The question becomes, what kind of registers do you want for status or for control, right? And how do you document how they are actually supposed to be used, right? Various things like how do you efficiently move data around, what are the abstractions that you need to provide in terms of software, are things that need to be sort of clearly defined as a system level designer. And as we can see, there are a few future trends that sort of come to mind, right? Increasingly, you will find that the hardware that's available to you has certain kinds of programmability. We very rarely build a digital design which has just a single function. You always want to provide some kind of programmability, meaning that there is at least some parameterizability or some tuning that you can do, right? Without that, it's very unlikely that you are actually going to be able to have a useful piece of digital design. From the software point of view, increasingly there is active research in the area of what are called hardware aware compilers, things that can actually sort of take into account the capabilities of hardware and then generate software that is able to actually make effective use of that. And finally, there are also domain specific programming models, especially nowadays when you look at things like the AI/ML domains. There are a number of custom languages, or even if not custom languages, there are definitely sort of libraries and modules like, for example, PyTorch and TensorFlow, which provide you almost something like a custom language that can be used to communicate or to program the basic ideas of what is required for AI/ML, which means that having hardware that is directly capable of sort of implementing some of those could in turn become a useful thing to have. And then writing modules in such a way, writing software modules in such a way that it makes effective use of the hardware is also sort of an iterative process that keeps improving.